you can hear me okay. So this is going to be a sort of a kind of an overview talk of my kind of own take on this question of where do solar eruptions come from. And I do apologize in advance if there's anyone who already saw this talk before. I have given it before. So what we were looking at on the first slide was, of course, a filament eruption in EUV. And here I'm showing you a movie of same thing from SDO. And probably most people working in solar physics are quite familiar with this idea that these erupting filaments lead to coronal mass ejections in CME. So you can see the filaments before they erupt, not only in ultraviolet, but also in H alpha, hydrogen alpha. And this is an example. And you see this big, long filament coming out of this active region 12280. And the thing about these filaments is that they're not randomly distributed over the solar surface, but they are kind of located at particular places. And those places are polarity inversion lines in the sun's magnetic field. So if I change here to a magnetogram, you're looking at the line of sight magnetic field. So white, it means it's coming out of the sun, black going into the sun. And you see that this big filament was located between the white and black. So along this polarity inversion line. Maybe I can try and blink between these. I don't know if this will work on everyone's connection, but you can see that the filaments are located along these inversion lines. So if we zoom in closer, you can see that there's more structure visible in the EUV. And if you have a good connection here, you might be able to see these kind of plumes or fibrils that you see in the EUV. They're indicated by the yellow arrows in this right-hand picture here. And you see that those fibrils are not only in the filament itself, but in the what we call the filament channel around it. So it's this filament channel that's somehow the more fundamental structure. And what it's telling you is that the magnetic field is going essentially along the channel, so along the inversion line, as opposed to being transverse to it. And it's in these locations that you see filaments. So here's another picture of a filament, again in EUV. This is a nice movie made by David Long, where he's processed it to kind of enhance the contrast. And one thing that you see nicely in this movie is that the structure of the filament, when it erupts, gives you the impression of kind of twisted magnetic field lines. And these, see there you see, so I think during this movie there's two separate eruptions. We're starting again here, and you can kind of look out for twisted kind of helical structures. There you go. And what that's telling us is that this structure is containing electric current. So the dark filament material is sort of denser material, and it's sitting in this twisted magnetic structure, so we believe. And the reason it's twisted is because it contains electric current. So if you're not a solar physicist, you're probably more used to thinking of magnetic fields as kind of smooth laminar kind of objects. So like if you have a bar magnet, the magnetic field around it has this beautiful smooth pattern. And this is similarly, this is what we call a potential field model for the sun at some particular time. And it's characterized by having all of the source currents inside the sun. So you don't have these currents in the corona, and that means you have a nice smooth potential field. Whereas what the filaments are telling us is that the real corona does contain, at least in some places, currents and that are generating more complex, kind of twisted magnetic structure. So I'm going to briefly in this talk suggest that there's a kind of a three-step process going on here. So that the basic coronal evolution consists firstly of the injection of magnetic helicity by surface motions. So magnetic helicity is basically the technical way of measuring this twist and shear, if you like. And this helicity collects at the polarity inversion lines, forms these filament channels that we see. And then the coronal mass ejections act to remove helicity by essentially erupting these filaments out into planetary space. So what I want to do is just sort of flesh out this picture a bit. I'm not going to talk about the dynamics of the eruptions themselves, because a lot of other people work on that. But what I'm more interested in is how the free magnetic energy, as it were, gets there in the first place. So we need to understand a bit more about what this magnetic helicity actually is. I don't want to get too technical, so I'll try and define it by cartoon. Here, this is as complicated as the formula you're going to get, but the helicity of a magnetic field is just the net linkage of magnetic flux. So if you imagine that your magnetic field is divided into discrete flux tubes with fluxes phi I, then you basically sum over all pairs of those tubes the product of the fluxes and this coefficient Lij. And this coefficient Lij is what's called the Gauss linking number. So imagine you have three flux tubes like this. So this Gauss linking number is something that's defined for closed curves. So you have three magnetic flux tubes. So if I take, for example, tubes 1 and 2, I can calculate their linking number. One way to calculate it is to look at the number of crossings, signed crossings, and count them. So if you look at the thing from some particular angle, as we are here, you can see from this angle there are two positive crossings between tubes 1 and 2. So the sign reflects which orientation. If you go, because the curves have a direction, the magnetic field direction, you can assign an orientation. I can never remember which one is plus and which one is minus, but hopefully I got it correct here. You count those crossings. So in this case, there's two crossings. So you say, okay, Lij is that 2 divided by 2, so 1. So in other words, they're linked once. And you can see, of course, the curve goes through, the curve 1 goes through curve 2. And similarly, it goes through curve 3, and when you add them together, you get this expression for H. And the factor of half is just because you count each pair twice in the double sum. So that's essentially the helicity. It's a linkage. This is just another example. Here we've only got 2 tubes, but you count 4 negative crossings, so the helicity is -2 times the product of fluxes. So the thing about helicity is that you can't change it unless the tubes reconnect with each other. So if the only way you can change this number is to allow them to pass through one another. And this is actually a manifestation of the well-known Alfvén's theorem, that magnetic flux tubes preserve their topology in a perfectly conducting plasma, and you have no reconnection. And this is actually Alfvén receiving the Nobel Prize for his work on MHD. Now, if it's impossible for the tubes to pass through each other, then how does the helicity get there in the first place? And the answer is a little bit technical, and it gets there by being injected through the boundary. It comes from inside the sun. And this is only possible because the field lines in the corona are not closed curves within the corona. They tend to actually end on the solar surface. And when you have a field that ends on the solar surface, you can't compute the helicity unless you somehow complete the curves. So in solar physics, we use this famous idea called relative helicity that was introduced by Berger and Field in 1984. So incidentally, Mitch Berger, I think, is giving the next one of these seminars in a few weeks' time. But the idea of the relative helicity is that you say, right, well, I'm going to close my magnetic field with a potential field in the exterior domain. So here, the exterior domain is actually the inside of the sun, because we're interested in the helicity of the corona. And so you see in this movie, what I've done is generate a non-potential field in the corona, but I've computed a potential field in the inside of the sun so that I can complete the field. And the idea of choosing a potential extension is that that minimizes the extra kind of linking that you're going to get. And once you do this, you have a well-defined quantity called the relative helicity. So the question then is, how is this helicity injected into the corona by surface motions? And I think it's useful to look at a sort of simple cartoon here as well. So the example I'm going to look at is a sheared magnetic arcade, so a line of coronal loops. And in the kind of cartoon at the bottom, you can see this arcade is being gradually sheared. So there's an opposite velocity on either side. So you're building up essentially shear or electric current within the arcade. And so if I draw it schematically, it basically looks like that. I'm trying to relate it back to the linking of field of flux tubes. So, okay, well, if you just took a potential arcade, you completed the curves in the interior of the sun in a potential way, and then you sheared the whole thing, then it would shear like this, and you see that you would generate no relative helicity because you've got the same number of positive and negative crossings. But the thing is that if you did that, you would generate current inside the sun as well as in the corona. So it would no longer match the relative helicity. So what you actually do when you calculate the relative helicity, I mean, no one does this explicitly, but what you are mathematically doing is extending the field with a potential field. And if I do that, you see that I get a net relative helicity. So in other words, I've created relative helicity by shearing this arcade. And it's precisely that mechanism that creates the helicity in the corona. So the idea is then that we can watch what's happening on the solar surface. So obviously it's more complicated than just shearing an arcade, but we can try and observe the velocity on the surface and find out how much helicity is being injected. And this is what you can do with modern observations. So the left-hand movie here from Zhudong's sun is using, I think, SDO data to infer the sort of horizontal velocity field on the solar surface. You can see the magnetic flux patches moving around within an active region. And if you do these calculations, you can now track the amount of helicity injected. The right-hand picture is actually a different way of estimating the helicity injection from Kevin Dalmas. Here it's what we call a nonlinear force-free extrapolation. So it's just a static model. You take a vector magnetogram, and you basically try and find a magnetic equilibrium that matches to that magnetogram. And then you can ask, well, what is the relative helicity of that magnetic equilibrium? And he's colored the individual field lines here, or the individual flux tubes, according to their relative helicity. So we have an idea now from doing these vector magnetogram observations over a number of years of how much helicity is injected. And there's quite a nice survey for solar cycle 23 by Labonte and collaborators, especially Manolis Georgoulis. And they basically looked at all of the largest active regions in cycle 23 and observed them while they were kind of on this side of the sun, and extrapolated an estimate of how much helicity is injected in these regions by the motions that you're seeing in this kind of movie. And you get about 10 to the 46 square Maxwells per solar cycle, roughly speaking. Now, the thing is that this is not the only source of helicity, because once your active region has emerged, it doesn't just disappear, it spreads out and decays over the solar surface and sits there for sort of the flux from that region remains there for months or even years. And during that time, it moves around, and that can itself generate helicity. So if we want to understand that, we can't do it solely from observations because we don't have magnetogram observations of both sides of the sun. So we have to have a model for how the whole solar surface is evolving. And this is something called the surface flux transport model. And what you're looking at here on the top is my implementation of this model. And I think we're looking here at solar cycle 23. And I'm comparing it on the bottom with synoptic magnetograms. And these are from, I think, Kitt Peak. So basically, you can't, the observed one, you can only make a map once every 27 days because you've got to wait for the sun to rotate around. Whereas the model is kind of continuously evolving. But I'm showing it here just for comparison. This kind of model goes back to Robert Layton, who in the 1960s was kind of the first person to notice or suggest that you could model the evolution of the flux patterns on the solar surface with a kind of advection diffusion model. So the advection comes from large scale flows. So the most noticeable one is the differential rotation. You can see all the patterns are getting kind of stretched into a banana shape by this differential rotation. And then the diffusion is a parameterization of the small scale flows, causing the flux to spread out. So nowadays we can observe quite nicely the small scale flows. So this is an SDO, or an example from SDO data showing you the sun's, what we call supergranulation pattern. So these red lines are the boundaries of the convective cells on some kind of time interval. And this box at the bottom is just a zoom into the middle. And so the red thing is actually showing you a Lyapunov exponent of this observed velocity field. So it shows you the cell boundaries, and then the blue one is the opposite Lyapunov exponent. So it's large, the lines are coming together at the cell centers essentially. But anyway, it's showing you the pattern of supergranulation. So this is not the finest scale of convection on the sun, but it's the scale that's most relevant for the magnetic field because the magnetic flux tends to concentrate on the boundaries of these supergranules. And you can see that in this observation here. So what they did here, if you have a good enough connection to see it, the white crosses are basically passive tracers. So they just put a load of quarks, if you like, floating on the sun, and then the observed velocity field moves them around. And what you see is that the quarks congregate on the supergranule boundaries. So the granules are kind of shown by different colors here, whereas the supergranular boundaries are shown by where the white quarks end up. And then just to make it even more complicated, the yellow and kind of cyan colors are showing you magnetograms, line of sight magnetograms. And from those, you can see that the magnetic field tends to congregate at the supergranular boundaries. So this is what's going on a smaller scale. And when you do the large scale model, Layton's idea is to treat this as a diffusion. So the magnetic flux is kind of randomly walking around as the convection pattern changes. And on a large scale, that looks like a diffusion. So that's why the active region spread out, essentially. So what we can do is try and estimate the amount of helicity injected by this surface flux transport model. And this is work that I've been doing, or I did recently with Gareth Hawkes, who is a PhD student at Exeter of Mitch Berger's. And he had been updating some earlier calculations done by Berger and Roosmaken, where they were trying to estimate how much helicity the sun was ejecting from differential rotation. And so that was just from observations. Here we introduced the flux transport model to sort of cover the full solar surface and deal also with the higher latitudes. And this is one of the results from our paper. I'm only going to talk briefly about any of these results, but if you're interested, you can always have a look at the paper. So the top plot is just showing you the usual butterfly diagram, if you like, of the radial magnetic field. You can see here I'm following 3 solar cycles, this particular model, so 21, 22, 23. You can see the polar fields reversing each cycle. The second plot is the helicity flux that we measure. And what you can see is that it's sort of opposite signs in each hemisphere. And that's because most of the flux is coming from differential rotation. That's the strongest input by far. And therefore, you get the opposite sign in each hemisphere. And you see that at the higher latitudes, there's really a systematic sign of helicity flux, basically because the sun is always rotating in the same direction. And then you get this pattern coming from the active regions. And it turns out to be actually quite a tricky balance to estimate how much the net injection of helicity might be in each hemisphere. And because the active regions, you can see, almost cancel themselves out, but in fact not quite. And so when you do the calculation, you find that there's something of the rough order of 2 times 10 to the 46 square Maxwells per hemisphere per cycle injected by solar rotation. So it's, you know, more than we measured in the young active regions, but, you know, same order of magnitude, let's say. So this component is certainly important, and it's dominated by the sun's differential, well, the sun's rotation, and in particular its differential rotation. So what happens to this helicity once it's appeared in the corona? Well, it gets accumulated, we think, at these polarity inversion lines and forms those filament channels. And the easiest explanation for this is this famous cartoon by Van Ballehoijn and Martins. So what they were trying to do here was explain how you form helical magnetic fields in filaments, prominences, and what they suggested was that it's caused by a combination of the kind of shearing motions on the photosphere and supergranular diffusion. So you can see how the shearing motions inject helicity, just like in our cartoon before. But then what the supergranular diffusion does is cause flux cancellation. So positive and negative patches of flux come into contact at the inversion line, the dashed line here. And when that happens, you get reconnection in the corona above. And the idea is that the sort of short loop in the panel D will more easily submerge, but you'll be left with this long sort of axial magnetic field along the polarity inversion line. And this horizontal field will sort of build up at this location because there's nowhere for it to go. So the green field lines are then the kind of next lot coming in by diffusion. If you get reconnection beneath the original one, then you're going to end up with a helical field. So that was their basic picture. So you're going to build certainly axial field along the polarity inversion lines and probably helical fields, provided that you have this small scale convection leading to flux cancellation. And you can model this numerically, and this was actually originally the topic of my thesis. Here I'm showing you one of these so-called magnetofrictional models where I model the whole coronal evolution with kind of simplified equations and try and track where the helicity essentially ends up. And I'm tracking it by coloring the field lines red and blue, just like in the force-free model we saw before. And this red and blue color is something called field line helicity. And this is basically the correct way to sort of localize the helicity. Just very briefly, it sort of corresponds to splitting our helicity sum, which remember used to be a double sum. If you take one of those sums on its own, then that's what the field line helicity is essentially. So this AI, that's the field line helicity of flux tube I. And in our example we had before, you can calculate what this would be. So for example, the field line helicity of tube 1, well, it links once with tube 2 and once with tube 3. So it's just phi 2 plus phi 3. Another way of thinking about it is just the magnetic flux passing through tube 1. Similarly, tube 2, the flux passing through tube 2 is just phi 1, and so on. So that's the field line helicity, and it's still a topological invariant, because you still can't change those fluxes unless you have reconnection. And I really don't have time to talk about it, but it extends to the sort of case of an open boundary in a similar way to the field, to the helicity itself. There's the other example. So what I did in my thesis was to try and compare this model to observations of filaments. And the idea here was that you can actually tell the helicity, or at least the sign of helicity of a filament, by looking at its spatial structure if you have high enough resolution observations. So at the time we didn't have SDO, we were working with H alpha data, but data where the resolution was high enough that you could see the kind of fibril structures. And if you can see the fibril structures, you basically know where the magnetic field is connecting down to the photosphere. And you can tell whether that's on the positive polarity side or the negative polarity side. And you can infer the structure of the filament. So Sarah Martin had this famous study where they showed that you can actually infer whether it's positive or negative helicity just from the structure without even knowing the polarity, by whether it has this kind of right-handed or left-handed pattern. Anyway, the key thing is that you can tell the handedness of the filament. And it basically corresponds to, does the magnetic field along the axis go upwards or downwards in this picture that we're looking at here? Right, so which direction, relative to the photospheric polarities, which direction does the field go? And that was the thing that we could compare with the model. And so here I'm showing you that. So in the bottom left-hand picture, I'm showing each polarity inversion line by a red and blue color, where that color is indicating this so-called skew, so whether it's left-handed or right-handed. And you can actually see, when you look more closely, it correlates with the sign of the helicity in the top picture. And it's a kind of a cruder measure, if you like. And the interesting thing here is the bottom right-hand plot, where I'm just building up a longitude average over time as we play the movie. And what you see really nicely here is that there's a clear hemispheric pattern, right? So in the north, it's blue on average. In the south, it's red. So in other words, the filaments have basically negative, or the filament channels have negative helicity in the north and positive in the south, predominantly. And this hemispheric pattern was actually known already for the chirality of the filaments, and the purpose of our work was to try and explain where it comes from. And we showed that this model that captures the van Ballenhoyn-Martens mechanism basically generates the observed pattern. And not only that, but if you look at the level of individual filaments, which I'm not doing here, it manages to generate a lot of exceptions to the pattern correctly. So it's not just that it's always blue in the north and red in the south, but the local conditions, it boils down to the local pattern of magnetic flux on the surface, can generate also exceptions. And then they get kind of, their helicity gets kind of amplified by the surface motion. So we think that is basically going on. Okay, there's the final picture. So something we've been looking at recently, just very briefly, is if you look at the high latitudes, so especially just after the polar field reverses, you see that there's a tendency to have the opposite sign. And that's on these kind of polar crown filaments, as we would call them. So east-west oriented inversion lines that go a long way around the sun at the higher latitudes, so 50 degrees roughly. And in the model, they tend to have the opposite skew, the opposite helicity. And at least in that declining phase of the cycle. And it's not clear whether that's seen in the observations. In the observations, you tend to not really observe much shear at those latitudes, although it's difficult to observe because of the kind of projection angle that you're looking at. So Spiro Antiochos suggested that maybe the reason the real sun has less of a strong shear at those latitudes is because there's helicity injection at the small scales that is competing with the tendency we have in the model. So this is the so-called helicity condensation mechanism. So their group have shown that if you have a systematic sign of helicity injected at small scales, then this will condense and you will basically leave behind an axial field on your polarity inversion line. So very similar to the larger scale mechanism, the Van Ballehoyn and Martens. But it happens also on a smaller scale. And they've shown that through numerical simulations. The only question is, does the real sun have strong enough net helicity injection at small scales? And the good news is that if you measure the vorticity, if you like, in the convection, you find that there is indeed a hemispheric pattern of the correct sign in the vorticity of the supergranular convection. Arises from the Coriolis effect, essentially. And very roughly speaking, the magnitude of this vorticity is about 10 to the minus 6 per second. So what we did, work with Duncan Mackay as well, was to simulate the effect of this in the model. So here I'm showing you the kind of control case, the original model where we don't have this extra injection. And you see that this, hopefully you can see there's a kind of a long east-west inversion line, or roughly east-west, where it's strongly blue, so strongly negative helicity, even though it's in the southern hemisphere. So this would be one of those exceptional regions. So when we put in a parameterization of this small-scale helicity injection, we find that it does indeed reduce that excess negative helicity. But in this case, it doesn't actually reverse it completely, even though we put in 5 times the observational strength of vorticity. So the jury's a bit still out as to whether this effect is strong enough to really make much of a difference, although it's going to make a difference to the kind of numbers. So that brings me to the last point. Hopefully I haven't run over too far here. This is the removal of helicity by CMEs. And an entire field of research here that I have sort of 1 minute to talk about. So I'm just going to mention one study that was done by my former postdoc, Chris Lauder. And this was using, again, the magnetofrictional model. And what we did here was just identify individual flux ropes and try to estimate how much helicity they were ejecting. So each of the dots, so this is another time latitude plot, and each of the dots is showing you an individual flux rope. And so they exist for some length of time. We're just showing them at their sort of peak time. And they're colored by the helicity they contain. And you can see again the hemispheric pattern showing up here. And what Chris did was to basically add up the amount of helicity in these erupting ropes. And you find that, again, it comes to about 2 times 10 to the 46 square Maxwells. So again, same ballpark, completely independent estimate, but same ballpark figure for how much helicity we were putting in. Of course, there is also helicity ejected along the open magnetic field lines. And that's not included in this estimate. But roughly speaking, things seem to balance out here. It seems to make sense. Of course, there's something we like to make more quantitative in future, but that kind of brings me to the conclusions. So I think we have this kind of general picture that's getting more and more accepted, that these filaments are storing essentially helicity, and then the eruption of those filaments is the sun's way of removing it. Because at the end of the day, if you have too much free energy, you can't possibly be in an equilibrium. So you've got to get rid of it somehow. But it's kind of interesting that it doesn't just send out helicity smoothly and continuously. It goes in these discrete bursts. and they are what cause all of our space weather and what have you. So that brings me to the end of what I was going to say. Hopefully I didn't go too fast, but hopefully it gave you a bit of an overview.